So last week we started with introducing electric charge. We basically said there were charges in the universe, in nature, and there are two kinds of charges. Like one is we call positive, the other we call negative. And we concluded that like charges repel and unlike charges attract. So we talked about the origin of charge, and which was atomic, and we introduced material classification based on their conductivity. We called insulators the objects or the matter that does not allow charge flow in it, and we introduced conductors in which charges could freely move. So we introduced some more concepts related to charge, and then finally we introduced Coulomb's law. Coulomb's law was an inverse score law that governs the magnitude and the direction of the force between two charges. It was like F is equal to K Q1 Q2 divided by R squared. R is the distance between the charges. Q1 and Q2 are charges, and K is some constant, which could also be written like 1/4 pi epsilon 0, where epsilon 0 is a known constant of nature, which is like a free space permittivity. So this week I want to start with introducing again the Coulomb's law, but in its like vector form. Okay. So basically here we introduce two charges. Let's call one Q1, the other one Q2. And suppose this is where we are. Let's say this is our origin, like, I don't know, with some coordinate system, X, Y, Z. And I want to call the location of the first charge R1 and the location of the second charge R2. And this difference between R1 and R2, like let's call R2 minus R1, which is this guy minus this guy, which is this guy, right? Given this, we can define the force as a vector on the first charge by the second charge, right? F12. That's what we use repeatedly. It's equal to K, which is the same constant 1/4 pi epsilon naught, and the charge is Q1, Q2, and the magnitude of this distance, which is this distance. Again, we use this notation. If there is no arrow, it means the magnitude, right? I think we can sometimes use explicitly like this, or I don't know, 2, but sometimes we may just write it R21, dropping the arrow. And this is like the Coulomb's law without any vector information. To put the vector information, we put this guy, R hat 21. Okay? And this is the unit vector along this guy. Okay? And the definition is like the vector divided by its magnitude, if you like. Okay? Now, let me introduce a concept called electric field. So what is electric field? Electric field is the force experienced by like a unit charge or by a infinitesimal test charge. So to get this, we can start from Coulomb's law, which is, let's say the charge is like Q, and we, like a given charge is Q, and we put like a test charge here. Let's call this small q. And we can start with the Coulomb's law. F is equal to K, big Q, little q divided by R squared. And we take the limit of this test charge goes to 0. Okay. If you take the limit of this, you are going to get something like this. So this is the electric field. Or you can just write it with like 1/4 pi epsilon naught. Okay. So why do we do this? I want to remind you, like we were having it at least like 200 years ago. It was like a tough concept to swallow, to have like a force that was acting at a distance, because the natural thing at the time was contact force. And when you have things like gravity or electric field that are acting without any contact, people had a hard time. And I think it was Faraday who introduced this concept like electric field. And when you have an electric field, you think of this charge as a field, as an electric field that permeates the whole space, like a cobweb, like this. And when you put another test charge, it kind of hangs on to this cobweb, and it is imagined as if it's like a contact between that test charge and that cobweb, which is connected to the charge. So it turns out this electric field, this concept of field, is more fundamental than the force itself. Okay, and if it is more fundamental in nature, you should actually write the force in terms of electric field, and that's easy. Given the electric field E, you can just get the force immediately like this. So now let's talk about these electric fields a little bit. We can actually pictorially represent this concept. The first one is actually like, let's start with like a positive charge. It's like here, and then you have these like lines emanating from positive charge. And we need to also put the direction to these lines. So in the case of positive charge, lines emerge from the positive charge and go to infinity like this. So if you have the negative charge, you have still the same lines, but the direction is reversed. Also observe that the density of lines, like lines per, if you like, unit area like this, determine the strength of the electric field. For example, this line and this line are closer together, or at least more closer than these two lines, these 2 points. What this means is there is like a higher density of these lines. That means the strength of electric field is stronger. So when you draw these lines, be careful. Try to just put more lines for stronger electric fields. Finally, we can also use this principle of superposition to draw these lines. If you have a bunch of charges put together, you can write the electric field of each, let's say this point, for example, from this guy, something like this guy, something like this guy, something like this, and do the vectorial sum to find the net electric field in this point. According to what those directions determined. I mean, in the negative, for example, I wanted to keep simple, and I said all of them are positive, but say one of them were negative. Let's say Q1 was negative, then I had to flip this one like this, and I had to not consider this. Okay, then it's still a vector addition of 3 charges. So calculate the total electric field A at a point A here, and B at a point B in this figure due to both charges Q1 and Q2. Okay, you have 2 charges, Q1, which seems to be negative, minus 50 microcoulomb, and there's Q2, which is like plus 50 microcoulomb, and the distances are known. This is known. This distance is known. This is also known. And we want to find electric field, the net electric field at point A. I think it was something like 8.99 times 10 to the 9, something like Newton, 10 to the 9 Newton meters squared over Coulomb squared. I want to find electric field at A. Maybe I can start, let's see. Let's calculate X and Y components. Exactly, right? We just decompose it in its Cartesian components and sum everything up. Let's do this with for A. E electric field at A due to charge 1 along, let's say, X direction is equal to K Q1 divided by, I don't know, R, let's call it A1 squared, and we need to multiply with cosine theta A1, right? And cosine theta is this or this angle. So I've calculated this and multiply with cosine to get that one. So this should be what? So 8.99 times 10 to the 9 Newton meter squared over Coulomb squared. Q1 is minus 50 times 10 to the minus 6 Coulomb divided by the distance, which is 60 centimeters, which is 6 times 10 to the minus 1 squared. This is meter squared. Okay. And if you do this, I think, let's see what I'll find. So this whole thing should be minus 1.25 times 10 to the 6 Newton per Coulomb. And I also need to multiply with the cosine. So let's, right, this is the magnitude. I have a cosine here, theta A1, cosine theta A1. How can I get the cosine? Right, the cosine of this angle, which is the cosine of this angle. And I already have the answer, right? This divided by this. So it's basically this 1.08. This is 1.08 times 10 to the 6 Newton per Coulomb. Now I need to do the same thing for EA1Y. Okay. Maybe this one is actually, okay. The signs, so this field, we know it's going to be towards the field. And let's call this distance positive X. And let's call this negative Y. So this is going to be positive Y, as it should be. Then I just didn't write any sign here. So for the Y component, it's going to be negative, I know, because it's going to be down, and that's like what I call negative. And it should be 1.25 times 10 to the 6 Newton per Coulomb times sine theta A1, which should be, okay, let's calculate sine, clear, 0.62 times 10 to the 6 Newton per Coulomb. Let's calculate exit 5, yeah, something like 52. Yes. Now I calculate E A due to 2, and this charge only has Y component, so we don't have to deal with cosines. And it's equal to K Q2 divided by RA to 2. This is equal to 8.99, 10 to the 9 Newton meter squared over Coulomb squared. Q2 is 5 times 10 to the minus 5 Coulomb, and this one is divided by 3 times 10 to the minus 1, maybe it's actually squared. So this is 9, and this is 2. 4.99 times 10 to the 6 Newton per Coulomb. Right? Now for finding this, so we need to find vector sum of this guy and this guy, but this guy we know in terms of its components. So let's subtract this from this, and let's take the square of this and what remains here to find the magnitude. So E A, the magnitude of electric field at A is equal to, so what should it be? It should be 1.25 squared. Oh, sorry, 1.08 squared. 1.08 squared plus 4.99 minus 0.62 squared, and take square root of everything times 10 to the 6 Newton per Coulomb. 4.5 times 10 to the 6 Newton per Coulomb. Okay. How about the angle? I also need to find this angle. Did anybody find any angle? Okay, angle is like what? Phi is tangent inverse EY divided by EX. That's equal to tangent inverse. So EY is equal to, let's do this one more time. EY 4.99 minus 0.62 is equal to 4.37 divided by EX, and EX is equal to 1.08. So divide this by 1.08, something like that. And inverse tangent is 76 degrees. Anybody else? Yeah, good, 76.1. Good job. Thank you. I just need to calculate E of B2, which is equal to 8.99 10 to the 9 Newton Coulomb divided by meter squared times 5.5 times 10 to the minus 5 divided by 16 times 10 to the minus 2, which is equal to what? This is 2.8. Oops. 2.8 times 10 to the 6 Newton per Coulomb. And I have two of these guys, like this one and this one, and the angle is, let's see what the angle is. It's cosine. I need to multiply with cosine, and take it twice, because there will be exactly the same thing like this. Charges are the same, symmetrically placed. So let's multiply with this cosine, which is 26 divided by 40 times 26 divided by 40 is equal to 1.8, and times 2, 3.65. Dot, dot, dot. E total is 3.68 times 10 to the 6 Newton per Coulomb along X direction. So now, okay, let me just introduce something different. So here, the charges were like discrete, right? So far, I was thinking about discrete charges here and here and here and here, and I told you you can use the superposition. And you can use a superposition even if the charge distribution is not discrete. Even if you have like a continuum of charges, you can use that. And for this, we need to, I want to introduce you how we calculate the electric field of a continuous charge distribution. I think the procedure is more or less the same. So suppose we have like the uniform charge distribution in some region like this, okay? Some given region and some given charge. And we are interested in the total electric field, let's say at this point. Maybe we could choose here or here or here, but I chose there. So to do this, I choose like an infinitesimal region like this here. And I look at the distance from this infinitesimal unit to the point of interest. And I write the electric field from this guy. Of course, it's going to have like some X and Y components. And I write this electric field like this. So dE is what? K is, I mean, it's the usual. dQ, like net charge in this little region, which is dQ is generally some density times volume divided by the distance, R. And to find the net electric field, we just integrate this over all points inside this region. And like this, right? It's like K, some density times like some area or volume integral divided by distance. And this whole problem boils down to taking this integral, okay? This one? Yes, I think I didn't write it to be lazy, but there should be like some n of R. There should be some n of R. Maybe we can start with an example to this electric field calculation of a continuous distribution. So this is the example from your book. Suppose this is like a ring of charge. A thin ring-shaped object of radius A holds a total charge plus Q distributed uniformly around it. Determine the electric field at a point P on its axis, a distance x from the center, like here. Point P at a point x from its center. Let lambda be the charge per unit length, okay? We can write the equation for dl and then integrate it. Yes, exactly. So let's do this. I think this is like a good example. So we focus on just an infinitesimal region here. So your book chose here. I mean, you could choose any point. That's fine. You could choose here or here, and you could just do something like this, or like from here to here. I don't know. So your book chose this point. And the total charge, let's see what the total charge here is. So first, the charge density, lambda, by definition, it is total charge divided by total length. And total length is 2 pi times A. then the total charge in this little length, little segment, let's call it dq, is equal to, of course, it's like lambda times dl, but we know dl is equal to like a times d theta. So this whole thing is, and lambda is here. So this whole thing is q divided by 2 pi a times d theta. And you can cancel these. And you have dq. Exactly, right? Now I want to write the electric field. dE, I'll look at the vectors in a minute, is equal to k. dq, I just calculated dq. It's like q over 2 pi times d theta and divided by r squared. But in this case, r squared is this r squared, right? And I can calculate this guy from square of this plus square of this. R squared, okay, let me, x squared plus a squared, and that's it, okay? Right, integrate from 0 to 2 pi. So I will do the integration, but I think q is given, right? Here it says plus q in the problem. Now what I should do is like this. So what is this quantity? This quantity I calculated is this quantity. It's like a vector quantity, like you just pointed out. And if I integrate it in this form, I will get garbage, because it's like integrating a vector quantity as if it's like a scalar, right? So I have to decompose this guy to its components, like this, and I have to make integration for separate components. So for this component, it's just cosine of this angle, right? So this is dE, which is this. And I multiply it with cosine theta, which is cosine of this theta, to get dE along this direction. So let me do that. Cosine is like, I can just read it from this figure. Cosine is what? X divided by square root of x squared plus a squared. This is dEx, if you like. Exactly, right? And y component, so if you want to calculate the EY, it's the same thing times sine theta, which is A over blah, blah. But the thing about this y component is this. If you look at this point, this y component will point down. But every point here, like every point here, has a symmetry point like this, where electric field is like this, and its y component is in the opposite direction, right? So this point has a symmetric point here, and the electric field from this point is something like this, and its y component cancels, whereas its x component adds up, because x components are always pointing this way. But I think right now I claim that y component is 0, so I will only integrate x component. The first part is, okay, the first part is writing E without thinking about vectors, which is this part, right? I just write E, just using Coulomb. And my charge is dq, which is lambda times dl. Lambda is equal to q over 2 pi a, and dl is equal to a times d theta, and I find dq to be q over 2 pi times d theta. And the electric field definition was k dq divided by distance squared. And distance squared is this distance squared, which is square of this plus square of this. I have this. And I need to, okay, this is E, but I know E is a vector, and I decompose it to its components like this. And when I saw this, I immediately thought that, okay, there's like a symmetric point where this vector will point like this because electric field coming from this point is like this. So these two cancel. So I don't have to think about these perpendicular components. But now the nice thing is like the parallel components add up. So I can just put the projection, which is cosine of this. If you multiply this with cosine, you get the parallel component, which is this. And now I can integrate this guy to get the whole thing. So from now, I think if we agree on this, the problem is done. We are done here, right? So then I say Ex, I integrate. So the only thing that depends on the integral variable, the only thing that changes as you go from here to here to here is d theta. Everything else is constant. So I just take them out. So it's like k q over 2 pi x over x squared plus a squared to the power 3 over half d theta, and this is from 0 to 2 pi, right? And now I got this d theta is 2 pi. I can cancel this one with this one, and my net electric field is, okay, k q x over x squared plus a squared to the power 3 half, and it is along plus x direction. So dl, so okay, I mean it's here, right? So okay, let me convert dl. What is dl? Well, it's just the definition of dl, right? dl, if you have, maybe I can draw you a circle. If you have, oops, maybe I can use this one. If you have a circle, and suppose this is the center of the circle, and you have an r like this, and if you have like a very small angle, the theta, the length of this region is, of course, this is radius a times d theta, right? I'm confused that we already have a variable theta. Yes. So there is nothing to be confused. Look, yeah, the only variable here is theta, right? And the theta represents your location on the ring. So for any point on the ring, I have a variable theta. And for any infinitesimal interval, I represent it with d theta. And if you look at this problem, let's look at this problem. As you go along the circle, everything is constant. X is constant, right? Wherever you are, X is X. Wherever you are, the radius is also constant. It doesn't change. This R and this A is also constant. So the only variable is actually theta. So there's nothing to be surprised that you only integrate theta. Everything else just comes out as they are. I think for most of the class, we will probably have like these nice things, right? For example, so your book chose a nice, like a circle, which is like a rotational symmetric. Not only that, it also chose the point to be on that axis here. So if you have the appetite, I challenge you to calculate the electric field in a little bit of off-axis here, right? Let's see. I mean, you can, if you have time, energy, and motivation, you can try to calculate this one, and you'll see it's going to be a little bit harder than this. So the answer is, I think you may have irregular shapes, but I'm pretty sure there'll be some trick. So most of the time you'll have nice symmetric shapes. Now I want to ask you a couple of questions as a follow-up, okay? So if I put this charge right in the center of the circle, what is the net force? Maybe I can do it here, which is nicer. Suppose I have, okay, let's close these guys. So suppose this guy is again plus Q, and I put like a test charge plus Q here. Okay. The net force is 0, right? Yeah. So the net force is 0 on this charge. Then my question is it in equilibrium? Like this is like a plus, this guy is plus, like the circle, the ring is charged with positive charge, and my test charge in the center is also positive. Is it in equilibrium? Yes or no? Yes, right? Good. Let's put a tick. It's in equilibrium. The second question is it like a stable equilibrium or unstable equilibrium? Stable, yes or no? Is it stable equilibrium? No, right? Why? Let's put a no. It is no because if you just perturb this charge just a little bit, if you just move it just a little bit, you will have this force, which is outward. So if you just, maybe I can draw you, like if you look at the ring from like horizontal, you're going to see this line. And if you put that charge just a little bit like this, now it's going to start experiencing this force. And this force will only drive it away. So it's going to just go away from the center. That's why it's unstable. Yes, because it doesn't tend to return to its original position. Now let's change this. Let's change this to, I don't know, maybe it's easier to think of this to be minus. So let's ask the same questions. Is it in equilibrium? Yes. Is it stable? It's unstable. You are saying it's unstable? Stable, it is stable now. So it is stable now, and the reason is, okay, it's the same thing. If you, okay, this, I will remind you, this is like plus Q, this is minus Q, and you perturb it just a little bit and release. When you release, the force on this minus charge from this ring will be along this direction. It's going to restore. So when it comes back to its position after this tiny perturbation, we say it is stable. Okay? So if this is minus, this is plus, it is in equilibrium and it is in stable equilibrium. All right? Simple stuff. Wouldn't it be closer to one side and that side pull it more? Yes. So basically we are thinking of it to be along this line. And we are not thinking about this one side or another. So it's like always on the symmetry axis, okay? This is the nice thing about this configuration. So like I said, I suggest you think about this. Maybe you can start from here, right? You can say you are in a circle, completely inside the circle. You will see the kind of problems you have with integrals. Like if you have like a circle, let's say this is the symmetry axis, like this. And so far, our charge was here, right in the center. I'm not saying do it, but think about this. Like put your charge a little bit off center here. And let's see what happens, okay? So at least for the moment, I'm not interested in that. So of course, the idea is, right? You're right. Let's think about this. It's actually, it'll be a nice cancellation, but I think like for every charge, okay, let's say this is positive. Let's think about this. This is plus Q, this is minus Q, right? So everything will be, okay, it is kind of like this. So I think the idea is like there are charges here, right? And you are closer to these charges, and these charges are pulling it this way, and this way. And you are saying, oh, this side is closer, so it should move this way, but it's actually not like that. If you think about this, the effect from these sides, I think you can separate it like this. There are two sides. One side like this, the other like this. It's true that you are closer to this side and you may think like this side is going to pull it more and this side is going to pull it less, the distance is more. But the key idea is there is more charge here to pull it back. Okay, there's more charge to pull it back. So this amount of charge on this side compensates what's lost from distance. Yes, it's farther away, but there's more charge. And on the other hand, there is less charge here, but the distance is less. So at the end, it is going to be restoring if you have a minus charge here. Of course, this is like a pictorial way of seeing this, but I suggest you deal with integrals and see what happens. You'll see it's in stable equilibrium. Does that make sense? There were two thetas that we were dealing with. I'm not sure I understand. What is that? There were two thetas. There is only one theta, right? Oh, I see. Yes. Now I see. Yeah, I think maybe I could use like this one. Okay, thank you. So this theta, maybe I can use it like this. Okay, good. Okay, let's call this phi. Okay. This phi is this angle. So this phi, I see your point. I didn't even see that. This is phi. Okay, good. This is phi. I think now it makes sense, right? Got it. Thank you. Yeah. You're right. I think it's not good to. I mean, I somehow managed to get the right answer, but if I think I was lucky in some cases, I could mess up with thetas. Good job. Let's do this line. Okay, I'll delete this. Suppose you have a line like this. So a long line of charge. Determine the magnitude of electric field at any point P, right here, a distance x from the midpoint of a very long line, a wire, let's say, of uniformly distributed positive charge, like this figure. Assume x is much smaller than the length of the wire, and lambda be the charge per unit length. I think for the simplicity, let's imagine this line goes from minus infinity to plus infinity. It's infinitely long. And we are interested in the electric field at the distance x away. Okay, the first thing, without doing anything, we should, exactly like you said. So okay, two things. One is, what is dy? Okay, dq, sorry. Maybe I can write it. dq, we need to write dq, right? And the second suggestion is omit dey. Why? Do we have to deal with dey here? So the idea is, since this is like symmetric, for every point here, there is another point here, right? And for this point, electric field points like this, and its y component is like this. But for this point, electric field is like this, and its y component is like this. So this guy reasonably cancels with this guy. So if this one, we are good, right? So we can only focus on electric field along x direction, which is radially out from the axis of this line. If you think of this line like this, and if you think of like this, like circles, for any point on the circle, it's going to be like this, radially outward, which is a nice thing. And this is only due to the symmetry, okay? This makes sense, right? We all agree with that. Now I will come to the second point. What is dq? dq, what is given? What is given is lambda, and lambda is charge per unit length, Coulomb per meter. Then dq is basically dy times lambda. You can look at the units. dy unit is meter, lambda unit is Coulomb per meter. So I have Coulomb as I should. Now let's write this dE. It's along x direction. The other component cancels, adds up to 0. So it's only the x component. It's equal to k dq, which is dy times lambda divided by distance. Distance is this guy, square of this plus square of this. X squared plus y squared. And I also need to multiply with cosine, right? So cosine of this is equal to cosine of this, which should be equal to x over square root of x squared plus y squared. So if I integrate, e x should be equal to, so let's take everything independent of integral. So x is constant, right? X doesn't change with integral, only y changes. So I can take it out. Lambda I can take out, k I can take out. So it's something like that. K lambda x, so dy 1 over x squared plus y squared to the 3 over 2. So I want to put this integral in dimensionless form, right? I want to, so this right now, okay, maybe I can ask you, what is the limits of dy? So what should I put here and here? Where does this integral go from and where does it go to? Yes, good, thank you. It's minus infinity to plus infinity, right? Now I want to put this integral in dimensionless form. Let's do this. I will push this guy just a little bit. So to do this, I want to take this x out. something like this, right? So if I take this x out, it's going to be, maybe I can write it one more time, just for you to see. Oops. I'll take this guy to here. Is equal to k lambda x. I just write the same thing one more time, dy, but take x outside. X to the cube, 1 over 1 plus y over x squared, 3 over 2, right? And I also put one of the x's here. So I will put 1x here. I'll take this x squared, and I want to take this x squared actually outside. This is x squared. So now I can delete this. Now I want to call y over x u. So this is minus infinity to the plus infinity. Let's call u is equal to y over x. Du is equal to dy over x. So this integral will be, okay, this nicely cancels. This is k, oops, k lambda over x du minus infinity to plus infinity 1 over 1 plus u squared to the 3 over 2. Now, okay, what do I do about this integral? Yes, look, if you look at your book, there is like some tricks to deal with this integral, to put it in a form that you can integrate. But I don't care. I actually call this constant. Okay, who cares? And I want to say, okay, this is a number, right? Whatever this integral, you can integrate, and what you find is just a number. So in electric field will be k lambda over 2. Sorry, lambda over x. Now, if you are like desperate, like you can just go to like, I think, let's see if I can do that. You can go to Wolfram Alpha, because I don't want to deal with integrals. I'm not here to do the integrals. You can go to your calculus class. But let's do something like that, right? 1 over, let's see if Wolfram Alpha will help us. This is to the power, what? 3 over 2. This is 1 plus u squared. And let's see, comma x minus inf to plus inf. Fingers crossed. Let's see. There you go. It's here, right? That's the integral I want. And it finds what? Did I mess up here? Oh, it's not x, it's u. Sorry. It's u. This will converge. Yes, this guy, right? Minus infinity plus infinity. Do I have the same form? Yes, exactly the same form. It's equal to 2. So I can go back, which is this guy. I don't care, it is 2. So I can delete this proportionality and put equal sign, and I can put 2. Okay. And let's write with k. K was what? K was 1 over 4 pi epsilon naught lambda over x times 2, which is equal to lambda over 2 pi epsilon naught times x. Okay. So I suggest, I think it is very likely you'll find yourself in situations like this. There'll be some complicated integral and you'll forget about physics and it'll be like, oh, okay, let's do integrals. You don't have to do that. Let's cut some unnecessary parts, especially thinking that you are like, now everything is in front of your computer. You can get away with these nasty integrals. But if you really care, there are tricks. Follow your book. You can convert this to cosine nicely, and you can integrate this without any Wolfram alpha or without any trick. And if you can't do anything, it's just put it in dimensionals form like I did, and say this is just a constant. What is important is this proportionality. It's proportional to 1/x. Everything else is like factors. Where does x over root come from? It comes from here, right? So we first write electric field here, total electric field. And total electric field was total charge, which is lambda times dy, divided by distance squared, which was x squared plus y squared. And I had to project it to this axis because I knew this one will cancel with another one here. So I need to project it to find x component. And x component is cosine theta, and cosine theta is x over x squared plus y squared root, like this. And total integral comes down to this. I took x outside, dy x squared plus y squared to the power 3/2. So I want to point out one thing which is important. So if you had a point charge electric field was going like r squared, right? The distance squared, 1 over distance squared. This is point charge. Now line charge is going like 1 over distance r, which is, we showed x here, okay? This is important, okay? Just keep this in mind. Let's calculate the electric field of a disk. What else do I have here? So given a disk like this, and I again put like a plus q on the disk, and I am interested in the symmetry axis along here, which will always be the case, right? We don't care about these like awkward problems where you are here and you have to deal with some nasty integral. Like symmetry axis, and it's a disk. Hopefully it will be clear why we are doing this in a moment. Why we are only interested in these nice symmetry points. So the idea is, okay, the charge is distributed uniformly over a thin circular disk of radius r, charge per unit area is sigma, and calculate the electric field at point P. So the trick is I want to put like a ring. Now this is my infinitesimal. Why do I put ring? Can I just put like an elementary point like this? What is the point? What is the argument behind taking a ring? So I'm going to take a ring. I'm going to calculate its electric field, and I'm going to integrate over all rings. But why am I doing the ring? What is the reason? Any ideas? With ring, we can integrate only once. Yes. So there are a lot of reasons. Yes, we can integrate only once because we don't want to deal with double integrals. Ring is symmetric, but also I already calculated ring. Why don't I use my result here? Because I already have the result here, right? I want to use what I already calculated. There must have been a reason I did this. So I just put this here, paste. And now this is my, right? This is, let's just redo some of the things we need to, or let's convert this result to this problem. Now x is z. Oops. This is z, and this one is z. So radius is now r, not a. So let's put r squared. And dk times q is now the dq, right? So this one is dq, and this is dE, and this is equal. Now dq, I can write it. It's like area, which is dr times 2 pi r. This is area. And if I multiply with the density, which is sigma, I have charge. Let's do this. K dr 2 pi r times sigma 1 over z squared plus r squared to the 3 over 2. Now for E, I just integrate this. What is my integral limits? So now my integration variable is r. What is the integral limits? Yes, from 0 to r. From 0 to r. Let's see if we can take this integral. If not, we know what to do, right? So this is 2 pi k, okay, let's see. K 2 pi sigma from 0 to r dr times r, right? And 1 over z squared plus r squared to the 3 over 2. Now I want to do change of variable. Let's call again u is equal to z squared plus r squared. If I take the derivative of u, I got du here. Z is constant, so I have 2r dr. So whenever I see, okay, maybe I can put r dr is equal to du over 2. So this integral will be, I don't know, should I do this here? I don't want to spend a lot of space for integrals. So this is du over 2, 1 over u to the power 3/2, and the limits of u is when r is equal to 0, u is equal to z, right? Squared. R is equal to, and when r is r, u is equal to z squared plus r squared. And I think this integral is going to be what? 1 over square root of u minus, take from z squared to z squared plus r squared. Basically, we are done here. So this is equal to 2 pi k sigma, open the parenthesis, 1 over z squared, which is 1 over z minus 1 over square root of z squared plus r squared. I forgot z. Oh, yes, thank you. That's that's very important. I messed up. Sometimes it's better to take it slow. It's like z here. Okay, z here, And okay, Z, oops, thank you. And here, Z here, Z here. But this Z over Z is 1, so let's just put 1. Okay, good, thank you. That actually makes it much better. Thank you, good job. Now I want to take this, let's think about the limits. Let's think of like an infinite sheet like this. Let's take radius go to infinity. Then what my electric field will be, E is equal to 2 pi, let's write K2 1 over 4 pi epsilon naught sigma, and this guy will vanish, right? If you take R to infinity, this guy is 0. So that's basically it. So I can clean this up. 2 pi, this is 2. This is going to be equal to 1 over 2 sigma over epsilon naught. Now here, previously, there is something nice here, right? If we had a point charge, we had 1 over r squared. If we had the line charge like this, we had 1 over r in the previous page. So the power changed from 1 over r squared to r. And if you have like a sheet, like a planar charge, so what happened here should reasonably happen here too. So the power went from 1 over r squared to 1 over r. That actually happened, right? Electric field is constant. So there's no power dependence. Why we use limit and r goes to infinite? So I couldn't understand. So I wanted to say like this. I want to understand the electric field if you are very close to this plane. Of course, one way of doing this is letting that z goes to 0. Or I can just say that let's let r go to 0. I'm interested in this second limit. And this reason for the second limit is also I want to see how Coulomb's law changes for like a planar charge distribution. Because I find this interesting myself. If it's like a plane, and this plane goes to infinity on all sides, and I put a charge on top of this plane, what is the force on this charge? And what I find is like it's constant. It only depends on charge density on the plane. And I combine it with the previous findings, point charge, line charge, and planar charge, and they fit into this nice picture. 1 over r squared, 1 over r, and constant. You basically decrease r squared to r, and then 1 over r to constant. So I have a ring, and okay, let's put some symmetry axes. And in this ring, I want to choose this point. And this point is parameterized with some angle phi, and the infinitesimal in this point is like d phi. Okay, this region. And when I found the contribution of this point, I basically integrated this phi over all possible values from 0 to all the way to 2 pi. I didn't show this, but I think yeah, it would be nice if I draw this. Yes, you're right. So that's what it is, right? I integrate from phi 0. But the nice thing about this integral, there's nothing depending on phi, right? All right, then I think I'll finish it here. I'll see you guys next time.